Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module matrix diagonalization under the paper Mathematical Tools for Materials. So students, now let us see what we are going to learn in this module. Some of the relevant results about matrices are revisited and some new concepts have been introduced here. Scherer's theorem is stated. Positive definite matrices are defined and the criteria for positive definiteness stated. Power method for finding highest eigenvalue has been described here. The householder's method for tridiagonalization of a symmetric matrix is described. The QR algorithm for finding the eigenvalues of a symmetric tridiagonal matrix is also described. Now, methods of characteristic polynomial is elegant and useful for matrix or a very small order. The method is almost impossible to execute for matrices of large order. Finding the determinant of an n cross n matrix is computationally extremely expensive. Finding roots of the characteristic polynomial is equally difficult. So, from a numerical point of view, we are going to oblige to find other methods. Similar matrices. Two matrices A and B are said to be similar if a non-singular matrix S exists such as A is equals to S inverse B into S. Similar matrices have the same eigenvalues. If X is the eigenvector of A, then Sx is the associated eigenvector of B. If an n cross n matrix is similar to the diagonal matrix, it is said to be diagonalizable. An n cross n matrix A is similar to a diagonal matrix D if and only if A has n linearly independent eigenvectors. In this case, D is equals to S inverse A into S, where the columns of S consist of the n eigenvectors of A. The Scherer's theorem. If all the n eigenvalues of the matrix are distinct, the matrix A is diagonalizable. Even if the eigenvalues are not all distinct, the matrix may still have n linearly independent vectors and hence will be diagonalizable. In case it does not have n linearly independent vectors, it cannot be diagonalized. But the matrix can still be put in a triangular form, and that is good enough for our purpose. The diagonal elements of a triangular matrix are its eigenvalues. The tridiagonalization is ensured by Scherer's theorem, which states the following. Let A be an arbitrary n cross n matrix, then there exists a non-singular matrix U such that T is equals to U inverse A into U, which is an upper triangular matrix whose diagonal elements are the eigenvalues of A. Scherer's theorem is an existence theorem. It ensures the existence of such a matrix U but does not itself provide any meaning of finding it. Symmetric matrices. If A is a symmetric matrix, then there exists a diagonal matrix D and an orthogonal matrix Q such that A is equals to Q D Q transpose equals to Q D Q inverse. The converse of this theorem is also true. So now let us see its proof. Let A is equals to Q D Q transpose, where D is a diagonal and Q is orthogonal. Then A transpose is equals to Q D Q transpose whole transpose equals to Q transpose T equals to Q transpose transpose D transpose Q transpose equals to Q D Q transpose equals to A. Hence A is symmetric. To prove the converse, first consider the distinct eigenvalues of A. If Ax1 equals to lambda 1 x1 and Ax2 equals to lambda 2 x2, then lambda 1 minus lambda 2 V1 transpose V2 equals to lambda 1 V1 transpose V2 minus V1 transpose lambda 2 V2 equals to a V1 transpose V2 minus V1 transpose a V2 equals to 0. This implies that V1 transpose V2 equals to 0. Hence, we can choose orthonormal vectors for distinct eigenvalues by simple normalizing all these orthogonal eigenvectors. When the eigenvalues are not distinct, there will be subspaces of eigenvectors for each of the multiple eigenvalues, and we can find a full set of n orthonormal eigenvectors. Positive definite matrices. A matrix A is positive definite if it is symmetric and if x raised to power t or x transpose Ax greater than 0 for every non-null vector x. So let us see example, a matrix of 2 cross 2 having 2 1 1 4 elements. So this implies that x transpose Ax equals to x1 comma x2 2 1 1 4 into x1 x2 equals to 2 x1 square plus x1 into x2 plus x1 into x2 plus 4 x2 square equals to x1 square plus x2 whole square plus 3x square greater than 0. Here A is positive definite. The criteria for positive definiteness, a leading principal submatrix of an n cross n matrix A is a matrix of the form where AM is equals to A11, A12 up to A1M, A21, A22 up to A2M and so on till AM1, AM2 up to AMM. For every m lying between 1 and n, the theorem states that a matrix A is positive definite if and only if every leading principal submatrix of A has a positive determinant. Now let us see one example where A is 2 1 1 4. It has only two leading principal submatrices, A itself and the submatrix A1 A1 1. Determinant A is equals to 7 greater than 0 and determinant A1 is equals to 2 greater than 0. Hence, A is a positive definite. Another example, let A be a 3 cross 3 matrix having elements 2 1 0 0 3 0 1 0 4. Then the determinant of A is 24, which is greater than 0, and determinant of submatrix A2, which is having elements 2 1 0 3, is 6, which is again greater than 0, and A1 equals to 2, and determinant A1 is 2, which is greater than 0. Hence, A is a positive definite. The power method. Another useful criteria is provided by the following theorem. A matrix of symmetric n cross n A is a positive definite if and only if all its eigenvalues are positive. The power method. The power method determines the eigenvalues of a matrix with a large magnitude. By modifying the method slightly, it can be used to determine other eigenvalues. Many procedures for finding eigenvalues do not supply the corresponding eigenfunctions. The power method produces not only an eigenvalue but also the associated eigenvectors. The method is extremely simple in theory as well as in its implementation. Let A be a square matrix. Pick any vector x0 and start the successively multiplying it with A. Let lambda 1 be the eigenvalue with the largest magnitude and V1 the corresponding eigenvector. We assume that the x0 has a non-zero component of V1 in it. In that case, the claim is that with such a choice of x0, we find the eigenvalue of largest modulus by using the following theorem. Theorem. Suppose that the square matrix A has one eigenvalue lambda 1 which is greater in magnitude than all other eigenvalues, and let xn plus 1 equals to axn. Then for randomly chosen non-zero vectors x0 and a randomly chosen vector w, we have limit n tends to infinity w raised to power t x n plus 1 divided by w raised to power t x n equals to lambda 1. Moreover, the sequence of normalized vector xn equals to xn by mod of xn converges to the eigenvector of lambda 1. Now let us see its proof. Though the theorem is true in general, we prove it only when the matrix A is symmetric and the eigenvalue lambda 1 is simple. The proof of symmetric diagonalizable matrix is slightly harder, and the case of general matrix A is moderately harder. We can use the spectral theorem, that is, if V are not orthonormalized eigenfunction of A, then a is equals to summation I equals to 1 to n lambda I vi transpose. By multiplying successively by a, we obtain a raised to power n equals to summation I equals to 1 to n lambda I raised to power n vi transpose. Now further, from the equation we have xn equals to axn minus 1 equals to a n x naught. Therefore, on using the second equation, we have for any w transpose xn equals to w transpose a raised to power n x naught equals to w transpose summation I equals to 1 to n lambda I raised to power n vi transpose x naught equals to summation I equals to 1 to n lambda I raised to power n w raised transpose vi into vi transpose x naught, which is further equals to lambda 1 raised to power n w transpose v1 into v1 transpose x naught plus summation I equals to 2 to n lambda I raised to power n w transpose vi into vi transpose x naught. Since all other eigenvalues are less than lambda 1 in magnitude, so limit n tends to infinity w transpose xn by lambda 1 raised to power n equals to w transpose v1 into v1 transpose x naught. Assume that, like x naught, w also has a non-zero component of the eigenfunction v1, then limit n tends to infinity w transpose xn plus 1 divided by w transpose xn equals to lambda 1 raised to power n plus 1 into w transpose v1 into v1 transpose x naught whole divided by lambda 1 raised to power n w transpose v1 into v1 transpose x naught equals to lambda 1. This proves the convergence of the eigenvalues. So from equation second and third, we get xn equals to am x naught equals to summation I equals to 1 to n lambda I raised to power n vi into vi transpose x naught. Since the eigenfunctions are normalized, mod of xn equals to under root of summation I equals to 1 to n into lambda I mod raised to power 2n into vi transpose into x naught whole square. This implies that xn vector is equals to xn by mod of xn, which is further equals to summation I equals to 1 to n lambda I raised to power n vi transpose x naught whole divided by under root of summation I equals to 1 to n into lambda I mod raised to power 2n into vi transpose x naught whole square. On separating out the I equals to one part of the summation, xn vector is equals to lambda when v1 transpose x naught divided by mod of lambda 1 into v1 transpose x naught whole raised to power n into v1 plus summation I equals to 2 to n lambda I by lambda 1 raised to power n into vi transpose x naught divided by v1 transpose x naught whole into vi whole divided by under root of 1 plus summation I equals to 1 to n mod of lambda I by lambda 1 raised to power 2n into vi transpose x naught divided by v1 transpose x naught whole square. Since lambda 1 mod is greater than lambda I mod, where I is equals to 2 to n, this clearly converges. Now let us see one example. Consider the matrix of order 2 cross 2 where A is equals to minus 2, minus 3, 6 and 7. It has eigenvalues 4 and 1 and eigenfunctions 1 minus 2 and 1 minus 1. So choose x naught equals to 1 1 and w equals to 1 0. So x1 equals to a x naught equals to minus 2 minus 3 6 7 into 1 1 equals to minus 5 13, and likewise x2 equals to minus 29 61, and similarly x3 equals to minus 125 by 253 and so on. The corresponding W transpose Xn are respectively minus 5, minus 29, minus 125, minus 509, minus 2045, minus 8181. So from equation 4, the lambda 1 equals to limit n tends to infinity W transpose Xn plus 1 whole divided by W transpose Xn. The consecutive approximation to lambda 1 are 29 by 5 which is equals to 5.8, 125 by 29 equals to 4.310, 509 by 125 equals to 4.072 and so on. And the last one is 8189 whole divided by 2045 which is equals to 4.004. The last one is correct to 4 significant figures. Now next method is the householder's method. This is a method of reducing an arbitrary symmetric matrix to a tridiagonal form by a similarity transformation. A tridiagonal matrix is one in which, apart from the elements along the main diagonals and one diagonal above and below it, all other elements are 0. A is a matrix having A11, A12 and rest 0 0 0. Next column A21, A22, A23 and all other elements to be 0. Third row 0, A32, A33, A34 and so on. And we can finally get 0 0 0 up to ANN minus 1 and ANN. Once a matrix has been reduced to such a form, the QR algorithm reduces the tridiagonal matrix by a similarity transformation to a diagonal matrix. Since the householder method and QR algorithm use similarity transformation, the finally nearly diagonal matrix has the same eigenvalue as the original given matrix. For a symmetric matrix, there exists a similar orthogonal matrix Q such that D is equals to Q into T into A into Q. However, finding this transformation matrix Q is in general extremely difficult. That is why we take recourse to a circuitous route and convert the matrix to a tridiagonal form and then to a diagonal form by an iterative process. Householder transformation. Let W be a vector in space R raised to power n with unit norm W transpose into W equals to 1. The n cross n matrix P is equals to I minus 2 W into W transpose is called a householder transformation. Householder transformations are used to selectively zero out blocks of entries in columns of matrices. Now the theorem. A householder transformation P is equals to I minus 2 into W transpose is symmetric and orthogonal. So its proof P transpose is equals to I minus 2 into W transpose whole transpose equals to I minus 2 into W transpose into W transpose which is equals to 1 minus 2 W into W transpose equals to P. Further on, using the fact that W transpose W is equals to 1, we have P into P transpose equals to P into P equals to 1 minus 4 into W transpose plus 4 into W transpose into W transpose equals to I. So this implies that P transpose equals to P inverse equals to P. The first step is to determine a householder transformation P1 with the property that a raised to power 2 equals to p raised to power 1 into a into p raised to power 1, where p raised to power 1 equals to I minus 2 w into w transpose, has 0 entries in the first column of A beginning with the third row. That is such that aj1 raised to power 2 equals to a1j raised to power 2 equals to 0, and where j takes the value from 3 to n. The symmetry of aij raised to power 2 follows from that of A and the householder transformations. To choose the required p raised to power 1, we determined a column W such that W transpose W equals to 1 and which satisfies equation number 14. These two requirements together impose n minus 1 conditions on the vector W. To completely determine the vector W, we impose one more condition, namely a11 raised to power 2 equals to a11. This condition is satisfied by choosing W1 equals to 0. Now, a raised to power 2 equals to p raised to power 1 into a into p raised to power 1 equals to p raised to power 1 a into I minus 2w into w transpose equals to p raised to power 1 a minus 2p raised to power 1 a into w transpose. This implies that a raised to power 2 j1 equals to p raised to power 1 a j1 minus 2 p1 a wj into w transpose 1 equals to p raised to power 1 a j1 equals to p raised to power 1, where the elements a11, a21 up to n1 transpose. Because of equation 6 and 7, we have a2j1 equals to p1 into a11, a21, n1 transpose equals to a11 alpha 0 and all elements 0 transpose. We define vectors in R raised to power n minus 1 space and matrices in R raised to power n minus 1 cross R raised to power n minus 1. Unit vector W is equals to W2, W3 up to Wn transpose. Unit vector Y equals to A21, A31 up to An1 transpose. Unit vector Z A12, A13 up to A1n, where A is equals to A11, Z vector, Y vector and A vector, where unit vector W transpose into unit vector W equals to 1. P raised to power 1 is equals to I minus 2 W into W transpose equals to 1 0 0 I vector n minus 1 minus 2 W1 W unit vector W1 W unit vector transpose. So on solving this, we'll get 1 0 0 P unit vector raised to power 1 and P unit vector raised to power 1 equals to I unit vector minus 2 W unit vector into W unit vector transpose, where W unit vector transpose into W unit vector equals to 1, which implies that P unit vector raised to power 1 is a householder transformation in n minus 1 dimensions. Further, a2 equals to p1, a p1 equals to 1 0 0 p unit vector 1, a11 z unit vector, y unit vector, a unit vector into 1 0 0 p unit vector 1 equals to 1 0 0 p unit vector 1 into a11 z unit vector, p unit vector 1, y unit vector, a unit vector, p unit vector 1. So on solving this further, we get a11 raised to power 2, z vector raised to power 2, y unit vector raised to power 2, a unit vector raised to power 2. So this implies that a11 raised to power 2 equals to a11, y unit vector raised to power 2 equals to alpha 0 0 0, which is equals to p unit vector raised to power 1 into y unit vector equals to I unit vector minus 2 W unit vector into W unit vector transpose into Y unit vector equals to Y unit vector minus 2 W unit vector into W unit vector transpose into Y unit vector. Let W unit vector transpose into Y unit vector equals to R. So Y unit vector raised to power 2 equals to y unit vector minus 2rw unit vector. So on comparing the above equations, we obtain alpha equals to a21 minus 2rw2 0 equals to aj1 minus 2rwj, where j takes value from 3 to n. Now from equation 9, y unit vector 2 transpose y unit vector 2 equals to alpha 0 0 into alpha 0 0, which is equals to alpha square, which is further equals to p1 unit vector into y unit vector whole transpose into p unit vector 1 y unit vector equals to y unit vector transpose into p unit vector raised to power 1 into p unit vector raised to power 1 into y unit vector, which is further equals to y unit vector transpose into y unit vector equals to summation j equals to 2 to n a j1 raised to power 2. This implies that alpha is equals to plus minus under root of summation j equals to 2 to n a j1 square. So now from equation number 10 we get 2rw2 equals to a21 minus alpha, 2rwj equals to aj1, where j takes value from 3 to n, and 4r square into w2 square up to wn square equals to a21 square minus 2 alpha into a21 plus alpha square plus summation j equals to 3 to n aj1 square, which is further equals to summation j equals to 2 to n aj1 square minus 2 alpha into alpha 21 plus alpha square equals to 2 alpha square minus 2a21. This implies that 2r square equals to alpha square minus a21 alpha. To ensure that r square is equals to 0, only if a21 equals to a31 equals to an1 equals to 0, so we choose alpha is equals to minus sgn a21 into under root of summation j equals to 2 to n aj1 square. 2r square equals to summation j equals to 2 to n aj1 square plus mod of a21 into under root of summation j equals to 2 to n aj1 square. With this choice of alpha and r square, we finally solve the equations and we get w1 equals to 0, w2 equals to a21 minus alpha by 2r, wj equals to aj1 divided by 2r, where j takes the value from 3 to n. So on summary, we have given that A equals to A transpose equals to AI j, and alpha equals to minus SGN A21 into under root of summation j equals to 2 to n aj1 square, r equals to under root of half of alpha square minus a21 alpha, w1 equals to 0, w2 equals to a21 minus alpha by whole 2r, wj equals to aj1 by 2r, where j equals to 3 to n and p raised to power 1 equals to I minus 2 w into w transpose. With p raised to power 1 determined, the matrix A raised to power 2 is given by A into p raised to power 1 A p, and all the matrices are shown on the screen. The same process is now repeated for the second row, third row and so on. So alpha is equals to minus SGA A k plus 1 into k raised to power k into under root of summation j equals to k plus 1 to n a j k raised to power k whole square, r equals to under root of half alpha square minus alpha into a k plus 1 k raised to power k, w1k equals to w2k and so on up to wk raised to power k equals to 0. And likewise wk plus 1 raised to power k equals to a k plus 1 comma k minus alpha by 2r, and wj raised to power k equals to ajk raised to power k by 2r, where j takes the value from k plus 2 to n. The process is continued for k equals to 2 to n minus 2. This gives the desired tridiagonal matrix where A raised to power n minus 1 equals to P raised to power n minus 2 into A raised to power n minus 2 into P raised to power n minus 2 equals to P raised to power n minus 2 into P raised to power n minus 1 up to P raised to power 1 into A into P raised to power 1 into P raised to power 2 up to P raised to power n minus 2. Now let us see one example and consider a 4 cross 4 matrix shown on the screen. So alpha equals to minus SDN A21 into under root of summation j equals to 2 to n aj1 square equals to minus 3, and likewise r equals to under root of 7.5, w1 equals to 0, w2 is equals to a21 minus alpha by a2r, wj is equals to aj2 by 2r, where j takes the value from 3 to n, and p1 equals to I minus 2 w into w transpose, and likewise w1 equals to 0, w2 is equals to 5 by 2 into under root of 7.5, w3 is equals to 2 by 2 into under root of 7.5, w4 is equals to 1 divided by 2 into under root of 7.5. Now let us see the QR algorithm. Assume that the matrix has already been put in the tridiagonal form by the householder method. If A denotes the matrix of this type, we need not to use two indices for the various elements and therefore simplify the notation somehow by labeling the entries of A as shown on the screen. If B2 is equals to 0, then matrix A separates into two submatrices where A is equals to A1 0, 0, An minus 1. Here 0 are null matrices and An minus 1 is the matrix beginning with the second row and second column of A. So A1 is the eigenvalue of A and the problem is reduced to one of the n minus 1 dimensions. Similarly, if Bn equals to 0, An is one of the eigenvalues and the problem again reduces to one of n minus 1 dimensions. Finally, if Bj is equals to 0 for some intermediate value of j, 2 less than j less than n, the problem again reduces to two independent tridiagonal matrix problems. So, we can see these two matrices formed on the screen. Let us therefore assume that the problem has been reduced and none of the B's are Bohr rows, and the QR algorithm then proceeds as follows. First, form a matrix of matrices where A raised to power 1 equals to A, comma A raised to power 2 and so on. Second, A raised to power 1 equals to A is factorized as product, that is A raised to power 1 equals to Q raised to power 1 into R raised to power 1, where Q raised to power 1 is an orthogonal matrix and R raised to power 1 is an upper triangular matrix. Third, then define A raised to power 2 equals to R raised to power 1, Q raised to power 1. Fourth, the same process is then repeated where A raised to power I is factored as A raised to power I equals to Q raised to power I, R raised to power I. The product of an orthogonal matrix and an upper tridiagonal matrix respectively. Then A raised to power I plus 1 is defined by the product of same matrices in the reverse order, where A raised to power I plus 1 equals to R raised to power I into Q raised to power I. Since each Q is an orthogonal matrix, from the above equation we can write R raised to power I equals to Q raised to power I transpose into Q raised to power I into R raised to power I equals to Q raised to power I transpose into A raised to power I, where A raised to power I plus 1 is equals to Q raised to power I transpose into A raised to power I into Q raised to power I. Rotation matrix. Hence, transformation from AI to AI plus 1 is a similarity transformation. Since the matrix A is symmetric, it follows that all the matrices A2, A3 and so on are symmetric and have the same eigenvalues as A. The manner in which we define Qi Ri will ensure that Ai plus 1 will also be tridiagonal. We are now going from one symmetric tridiagonal matrix to another with the same eigenvalues. However, the process is such that the non-diagonal elements decreases sufficiently rapidly and the matrix tends to a diagonal matrix. Thus, it is an iterative process, such iteration providing a better approximation to eigenvalues. For the actual process of construction of the matrices, we first define the notion to a rotation matrix. This is not the general rotation matrix but a rotation in the ij plane of an n-dimensional space. In such a rotation, the aij, aji and ajj elements of the unit matrix 1 0 0 1 will be replaced by cos theta, sin theta, minus sin theta, cos theta respectively. Thus, our rotation matrix differs from a unit matrix in the four elements. Pii equals to Pjj equals to cos theta and Pij equals to minus Pji equals to sin theta for some theta and for some I is not equals to j, and I and j takes the value from 1 to n. Every rotation matrix, being a rotation in the n-dimensional space, is an orthogonal matrix. For any rotation matrix P, the matrix AP differs from A only in the ith and the jth columns, and PA differs from A only in the ith and the jth rows. The angle theta is a free parameter and can be chosen so that the ij component of PA is 0. The factorization of a raised to power 1 into q raised to power 1 into r raised to power 1 uses a product of n minus 1 rotation matrices to construct r raised to power 1 as r raised to power 1 equals to pn into pn minus 1 so on up to p2 into a raised to power 1, which is further equals to q raised to power 1 transpose into a raised to power 1. So for p2 we choose angle theta to be such that p11 equals to p22 equals to cos theta 2 and p12 equals to minus p21 equals to sin theta 2. Sin theta 2 equals to b2 by under root of b2 square plus a1 square equals to b2 by r. Cos theta 2 equals to a1 divided by under root of b2 square plus a1 square equals to a1 by r, where r is equals to under root of b2 square plus a1 square. This implies that a2 raised to power 1 to 1 is equals to minus sin theta 2 a1 plus cos theta 2 b2 equals to 0. The multiplication p2 a raised to power 1 affects rows 1 and 2 of a1. Thus elements 1, 3, 1, 4 and up to 1, n, which were zeros in a raised to power 1 to begin with, may no longer remains so in p2 a raised to power 1. However, since a raised to power 1 is tridiagonal, only the 1 and 3 entry can become non-zero. Thus, a2 raised to power 1 equals to p2 into a raised to power 1 equals to a1 by r b2 by r 0 0 minus b2 by r a1 by r 0 0 0 0 1 and so on into a1 b2 0 0 b2 a2 b3 0 0 0 b3 a3 b4 0 0 and so on. a1 square plus b2 square by r, a1 b2 plus a2 b2 by r, b2 b3 by r, 0 0 minus b2 square plus a1 a2 by r, a1 b3 by r, 0 0 b3 a3 b4 and so on. There is no change in the row 3 and up to n. As expected, the 1, 3 element is no longer 0. We follow the same procedure for P3, P4 up to Pn. In general, the matrix Pk is chosen so that the k into k minus 1 elements of a k raised to power 1 equals to pk into ak minus 1 raised to power 1 is 0. As a result, the k minus 1 comma k plus 1 elements will become non-zero. For pk, we choose the angle theta so that sin theta k equals to bk divided by under root of bk square plus ak minus 1 square equals to bk by r. Cos theta 2 equals to ak1 minus under root of bk square plus ak minus 1 square equals to ak minus 1 by r, where r is equals to under root of bk square plus ak minus 1 square. Here the coefficients bk, ak minus 1 refer to the coefficients in those positions at that stage of calculation, that is coefficient of matrix ak raised to power 1 equals to pk minus 1 minus p2 into a raised to power 1. At the end, all the entries below the diagonals will be 0 and not 1, but two subdiagonals above the main diagonal will become non-zero. Hence, we will end up with a special kind of upper triangular matrix where r raised to power 1 equals to a n raised to power 1 equals to the matrix shown on the screen. So, from the equations we have Q1 transpose equals to Pn into Pn minus 1 up to P2, and on taking the transpose we have Q raised to power 1 equals to P2 transpose into P3 transpose up to Pn transpose. A raised to power 2 equals to R raised to power 1 into Q raised to power 1. So from the above we have seen that matrix Q raised to power 1 is orthogonal. In addition, it is an upper Heisenberg matrix. A matrix H is an upper Heisenberg if Hij is equals to 0 for all I greater than j plus 1. That is, apart from subdiagonal, rest of the matrices below the diagonal consist of zeros. If Q raised to power 1 is upper Heisenberg and R raised to power 1 upper triangular, A raised to power 2 is also an upper Heisenberg. But we know that A raised to power 2 is symmetric, hence A raised to power 2 is in fact tridiagonal. The same way the matrix A raised to power 2 has been constructed from A raised to power 1, it can be shown that non-diagonal elements of A raised to power 2 will generally be smaller than those of A raised to power 1. So A raised to power 2 is closer to being a diagonal matrix. The process is now repeated iteratively. From A raised to power 2 we construct A raised to power 3 following the same steps and so on till the non-diagonal elements become less in magnitude than a pre-assigned smaller number. So students, let us now summarize what we have learnt in this module. We revisited some of the relevant results about matrices introduced earlier and introduced some new concepts. We also studied about the squares theorem in this context. We next defined the useful concept of positive definite matrices and stated the criteria for positive definiteness of a matrix. We then described the power method for finding highest eigenvalue in magnitude of a matrix. Though the method is general, we proved it for a symmetric matrix only. In another method of finding eigenvalues, a matrix is first converted into a tridiagonal matrix. We described the householder's method for tridiagonalization of a symmetric matrix. Finally, we described the QR algorithm for finding the eigenvalues of a symmetric tridiagonal matrix. Thank you.